All right, let's go through the classwork on the F test for variances as well as one-way ANOVA problems. You need open the Minitab file 292 ANOVA lecture as well as the 292 one-way ANOVA classwork. Both are attached to this video. So get those open and we will work through these, I believe, 4 problems. Yes, 4 problems. But as you notice with this document, there's lots of questions I can ask, especially when it comes to the quiz and the exam. So make sure you know how to answer all of these problems. Okay, let's start with an F-test problem. So a limo service offers limo rides from Lake Norman to downtown Charlotte. The CEO is considering 2 routes, one via I-75 and the other via I-85. He wants to study the time it takes to drive to the airport using each route and then comparing the results. He collected the sample data, which is reported in minutes. Using the 0.05 significance level, is there a difference in the variation in the driving times for the 2 routes? All right, that's your key word right there, variation. All right, that tells us that this is an F test for variances. All right, so what's our null and alternative going to be? All right, we've got we just want to test if there's a difference. So we're going to have, we can either, so you've got a couple options here, just so you know, you can type sigma, I'm fine with that, or you can go into insert symbol in your symbol browser, and you can actually add the sigma symbol if you want to. Again, totally up to you, whatever's easier. So we've got sigma for, let's say, I-75 equal to sigma I-85, and then that's going to give us an alternative of sigma 75 not equal to, so let's go up here and get our not equal to, sigma 85. Okay? All right, so what's the p-value of the test? So we want to run an F-test for variances. All right, we just have 2 samples. We have I-75 and I-85. All right, so we're going to go over to Minitab, and we can see our data over here in column C15 and C16. We want to go under 2 sample variances. All right. Are both samples in one column? No, if we had a situation like that, we would have all of our numbers in one column, and then in the other column, I-75 or I-85 as a sample ID. That's not what we have. We have each sample in its own column, all right? And this is going to be I-75 and I-85. We're going to go under options, all right? And under options, we are always going to leave the hypothesized ratio at 1, so we'll never have to worry about that. And with the alternative hypothesis, 99% of the time in real life, we are running a two-tailed test here. We are simply looking for, can we assume the variances are equal or unequal? So we will leave this on not equal to, all right? One thing you do want to do under options is you always want to check use test and confidence intervals based on the normal distribution. If you do not check that box, you will get 2 p-values and you won't know what to do. Okay, so again, make sure you check the use normal distribution box and say okay. All right, so it tells us up here that the F method was used, and we can scroll down to our test. This is synonymous to what we have written in number 1 for our hypothesis test. And our p-value is 0.0808. All right, what is the statistical decision? All right, since 0.0808 is greater than 0.05, we fail to reject the null. All right, what does it mean to fail to reject the null? All right. There is not enough evidence to conclude the variances are different. Okay, so on the exam, as well as the quiz, potentially. This is part one of a two-part problem. Part one will ask you, is there a difference in the variances? All right, that's what we just did. We concluded that there's not enough evidence to conclude there's a difference. And then part two will say, using the results, test if there's a difference in the means. So here, test if there's a difference in the mean driving times. All right, so now we have mu 75 equal to mu 85 versus mu 75, and we can just copy our not equal to mu 85. All right. We need to get a p-value for this test. All right, so we go under to sample t. All right, each sample's in its own column. We've got I-75 and I-85. We go under options. All right, we can leave the alternative on the default because that's what we're testing. We can ignore confidence level. But here's the million-dollar question. Do we assume equal variances? Well, what did we discover up here? There's not enough evidence to conclude the variances are different. Aha! So we can assume they are equal. And that's what we're going to do. We're going to assume equal variances. So we check our box and say okay. All right, and scroll down and we get a p-value of 0.8446. All right, since 0.8466, let's try that again, 46 is clearly greater than 0.05, we fail to reject the null. All right, what does this mean? There is not enough evidence to conclude the mean driving times are different. Okay, so that is an example of how you use the variance test to give you information to run a two-sample t-test for means. All right, let's take a look at number 2. John Smith manages a regional bank. He wishes to compare the productivity as measured by the number of customers served among 3 employees. 4 days are randomly selected and the number of customers served by each employee is recorded. Is there a difference in the mean number of customers served? All right, so let's look at Minitab for a second, and we scroll over to C18 through C20, Wolf, Williams, and Bennett. These are our employees, and those numbers represent the number of customers served. All right, so this is a very common question for a manager. You know, are my employees serving the same number of customers on average? Are they performing at the same rate on average? All right, so we want to write our null and alternative. All right, this is a one-way ANOVA problem. How do we know this is a one-way ANOVA problem? And the answer is we have 3 employees. We have more than 2. All right, so all employee means are equal versus an alternative, at least one employee mean is different or unequal. Okay. All right, we want the p-value. The p-value for this test. All right, so let's talk about how to run an ANOVA. All right, in Minitab. All right, we are going to go to ANOVA one way. All right, because we're only considering one factor, and the factor is employee. All right, and responses are in one column for all factor levels. No, we have more than one column. We have 3 columns, one for each employee. So we say responses are in a separate column for each factor level. And we want to select Wolf, Williams, and Bennett. All right, and under comparisons, we want to check Fisher. All right, so this is something you'll do each and every time you run a one-way ANOVA. You will put in your data and you'll go under comparisons and check Fisher and say okay. All right, so let's take a look at our output very quickly before we go back to the problems. All right, we get a null and alternative, just like what we have already typed in our document. All right, just like I told you in the PowerPoint, equal variances are assumed for the analysis. That is one of the assumptions of an ANOVA. We're told we have 3 levels for employee. In other words, we have 3 employees here in this problem. All right, this is what's called our ANOVA, or analysis of variance table. All right, and this gives us the p-value for this hypothesis test up here. Okay. We can keep scrolling down and we see R squared, which we are going to talk a little bit about. All right, remember R squared says, hey, does employee do a good job explaining the variation in customer served? All right, and then this is just sample data for our 3 employees, the sample mean, the sample standard deviation. All right, and then we get into the Fisher analysis. First we get grouping, then we get t-tests. These are adjusted t-tests so as to account for the buildup of type 1 error. And then we get the confidence intervals. All right, all 3 of these, the confidence intervals, the t-tests, and the grouping are all going to agree. Okay, they're going to explain to you when we consider the pairs, so Williams versus Wolf or Wolf versus Bennett, do they significantly differ, or can we assume they serve the same mean number of customers? All right, and what you're going to want to hone in on for me are the t-tests here, because I'm going to specifically ask you about a particular pair, and you're going to need the p-value for that pair. Okay, and we'll come back to that in a minute. And then the last thing in the output is the interval plot. All right, and with this interval plot, all right, we are going to interpret it with the Fisher analysis. All right, so we're going to interpret it with these p-values or with these groupings or with the confidence intervals. We're going to look at it coupled with that Fisher analysis to interpret, hey, is there a best employee? Is there an employee here that deserves a raise? And similarly, is there a worst employee? Significantly, statistically, is there somebody who's worse? All right, and again, we'll get back to that in just a minute. All right, so let's go back up here to our document. All right, we've got our null and alternative. What is the p-value for the problem? So our p-value is less than 0.0001. What is the statistical decision? All right, and I don't think I told you on any of these problems, from this point forward, we're just going to be working with alphas 0.05. All right, so I think I did not type it in these problems. I did there. I did not in number 2. Okay, so it looks like sometimes I do, sometimes I don't. Well, just you're hearing me say that alpha is 0.05. All right, so since 0.001 is less than 0.05, we reject the null. All right, what does that mean? There's enough evidence, let's say that. There is enough evidence to conclude that at least one employee mean customers served is significantly different. Okay, that's all we get, guys, from the problem. At least one of them is different. So when we look at this p-value, we don't know which one. We don't know if they're all different. We only get at least one is different. We need to dive deeper. We need to look further into the analysis. All right, and that's where the Fisher analysis comes in. All right, so using the Fisher analysis, and I tell you what, let's add another problem in here. Is employee a good explainer? And I guess I shouldn't word it that way yet. Let's do this. Let's try. I just keep. I keep thinking of more questions. How about this? Discuss the breakdown and variation. Let's do that. All right, discuss the breakdown and variation. All right, so this is where we are going to look at R squared. All right, so R squared gives us how good employees doing. Okay, so 91.68%. How do we get 91.68%? All right, it is actually the adjusted sum of squares for the factor 992 divided by the total adjusted sum of squares. All right, so it is the, let me say this, factor adjusted sum of squares divided by the total adjusted sum of squares. All right, which is 992 divided by 1082 for this week, not next week, equals R squared, 91.68% of the total variation in customers served is explained by employee. All right, and from an analyst standpoint, that's phenomenal. All right, the fact that the variation in these numbers right here, okay, nearly 92% of the variation is explained just by Wolf, Williams, and Bennett. All right, that leaves some percent unexplained, right? All right, so 1 minus R squared, all right, will give us the unexplained variation. All right, so we've got, let's see, 8.32% of the total variation in customer served is unexplained. All right, and what might fall into unexplained variation here? That could be weather outside, time of day, mood of the customer. There's all sorts of, there's really infinite possibilities for what is unexplained. All right, so using the Fisher analysis, is there a difference between Williams and Bennett? State the hypotheses, p-value, decision, and conclusion. All right, so what we want to do now is scroll down to our Fisher individual tests of means table, okay? And we are interested in Williams and Bennett. I don't know why. All right, so we take a look at Williams and Bennett. All right, that's the last one here, and we see that p-value. All right, so we're going to have mu Williams equal to mu Bennett versus an alternative of mu Williams. Let's see here, we need to insert our not equal to. Mu Bennett. All right, the p-value equals less than 0.001. All right, so what's our decision there? Since 0.0001 is less than 0.05, we reject the null. All right, what does that mean? There is enough evidence to conclude that Williams and Bennett serve a different mean number of customers. Okay. All right. So the next question's a bit loaded. All right. Using the Fisher analysis and the interval plot, is there a best employee? Okay. So let me expand this a little bit. Let's scroll down to our interval plot. Okay. And when you're looking at this, what you see is that Williams, the middle one here, what this is, the blue dot is his sample mean, all right, and then these bars represent a 95% confidence interval for the population mean number of customers served by Williams. And notice Williams is way up here above Wolf and Bennett. But before you can say Williams is the best, you have to make sure that Williams is significantly different from Wolf and Bennett. Well, we already know from our t-test over here that Williams is different than Bennett. Okay, so we can go back up to our table, and we know from this less than 0.001 that Williams and Bennett are different. We also need to look at Williams and Wolf. Well, that p-value is also 0.001, which is a significant p-value. So Williams is significantly different from Wolf. So since this the first p-value here and the last p-value here are both less than 0.005, and Williams sits atop everybody, we can say that Williams is the best employee. All right, now is there a worst employee? Well, again, we come back to our interval plot, and it looks like Bennett is way down here below everybody else. But we have to make sure that Bennett is significantly different from Williams and significantly different from Wolf. All right, so we go back up to our t-table, and we look at our two p-values involving Bennett. We already know Bennett and Williams are significantly different. We look at Bennett and Wolf, and because the p-value 0.006 is less than 0.05, Bennett and Wolf are also significantly different. And so Bennett is significantly different from the other two and less than both of them. So we can say that Bennett is the worst employee. All right, so again, I think if there's any confusion right now with you guys on these questions, we'll clear them up as we work the next two problems. All right, and let me just go ahead and add this other question. Discuss the breakdown in variation, because we want to make sure we do that on these problems. All right. Question 3. Recently, airlines cut services such as meals and snacks during flights and started charging for checked luggage. A group of 4 carriers hired a marketing research company to survey passengers regarding their level of satisfaction with a recent flight. The survey included questions on ticketing, boarding, and flight service, baggage handling, etc. 25 questions offered a range of possible answers from 4 excellent to 1 poor. These responses were then totaled, so this total score was an indication of the satisfaction with the flight. The highest possible score was 100. The marketing firm randomly selected and surveyed passengers from the 4 airlines. Is there a difference in the mean satisfaction level among the 4 airlines? All right, so let's take a look at our data for a second. We have Southwest, AirTran, Delta, United. How do we know this is going to be a one-way ANOVA? Because we have 4 airlines. All right, we have more than 2. All right, so this makes it a one-way ANOVA. All right, so we've got our null. Versus our alternative. All right, so we can go into Minitab now and run our test. So we've got ANOVA, one-way ANOVA, Responses are in a separate column as we see from C1 through C4. So we check Southwest, AirTran, Delta, United. We go under comparisons and check Fisher and say OK. All right, so we see that the null and alternative match what we've written in our Word document. All right, we scroll down to our ANOVA table to get our p-value for this test. So our p-value for this test is 0.0007. All right, since 0.0007 is less than 0.05, we reject the null. All right, what does that mean? All right, there's enough evidence to conclude at least one airline mean is different. Do we know which one? Nope. Do we know if it's all of them? Nope. We only know at least one is different. All right, discuss the breakdown and variation. All right, so we see with R squared, we get 59.98% of the total variation is explained, of the total variation in customer satisfaction. You always want to say what is the variation. So the total variation in customer satisfaction is explained by airline alone, the brand. All right, and that leaves 40.02% of the total variation in customer satisfaction is unexplained. All right, using the Fisher analysis, is there a difference between Delta and United? All right, so is there a difference between Delta and United? All right, so we've got a null, mu Delta is equal to mu United versus an alternative, mu Delta. And I'm just going to go up here and copy my mu United. Okay. All right, so Delta United. So we go down to our Fisher individual tests for differences of means. We're interested in Delta United. All right, so we go down to the very last pairing here, and our p-value is 0.2433. All right, so since that's the p-value, what's our decision? Since 0.2433 is greater than 0.05, we fail to reject the null. All right, what's that mean? We cannot conclude there is a difference get that word spelled right. All right, we cannot conclude there is a difference in the mean customer satisfaction between United and Delta. All right, so again, the population means could be equal for Delta and United. All right, the loaded questions. Using the Fisher analysis and the interval plot, is there a best airline? All right, so let's take a look at our interval plot. All right. We clearly see that Southwest is the highest. All right, so we want to say Southwest is the best. But before we do, we need to make sure it's significantly different from AirTran, Delta, and United. So let's go back to our table of t-tests and look at all of our Southwest pairings. All right, AirTran and Southwest, take a look at this p-value. That p-value is less than 0.05. So AirTran and Southwest are different. Delta Southwest, that p-value is 0.0008, less than 0.05, so Delta and Southwest are different. United Southwest, p-value 0.0001, less than 0.05, so United and Southwest are different. So Southwest is significantly different from the other three airlines, and Southwest sits atop the other three, so we can say that Southwest is the best brand for customer satisfaction. All right, is there a worst? All right, so it looks like United is the worst, right? United is the lowest. All right, but is United significantly different from the other three? Well, we go up to our t-test, all right, and we see we already know United and Southwest are significantly different because the p-value 0.0001 is less than 0.05. United AirTran, significantly different because 0.0165 is less than 0.05. Aha, but we come to the one we've already looked at, United Delta. Here we failed to reject the null, all right? We could not conclude that United and Delta are different. So since United and Delta cannot be considered different, there is not a worst. All right, so we simply say, no, there is not a worst airline. Why? Because Delta and United are not significantly different. All right, last problem. Citrus Clean is a new all-purpose cleaner being test marketed by placing displays in 3 different locations within various supermarkets. The number of 12-ounce bottles sold from each location within the supermarket is reported. At the 0.05 significance level, is there a difference in the mean number of bottles sold at the 3 locations? All right, how do we know this is a one-way ANOVA? Because we have 3 locations. If we look in Minitab, we have near the beer, near the bread, and other cleaners. All right, so we want to come up with our null and alternative for the ANOVA. So all location means are equal versus at least one location mean is different. All right, what's the p-value for the test? So we go under ANOVA, one-way ANOVA. All right, everything's in a separate column, so we put in near the bread, near the beer, and other cleaners. We go under comparisons and check Fisher and say OK. All right, we scroll down to our ANOVA table, and here's our p-value for our ANOVA hypothesis test. So our p-value is less than 0.0001. All right, since less than 0.001 is less than 0.05, we reject the null. What does that mean? All right, we can conclude at least one location mean is different. Do we know which location? Do we know if it's all locations? No, we don't. We don't know anything more yet. All right, discuss the breakdown and variation. All right, so we take a look at R squared. So does location do a good job explaining the amount of Citrus Clean sold? Yeah, it does a pretty good job. 87.49% of the total variation. All right, so roughly 80%, all right, so roughly 80% of the variation in how much Citrus Clean you sell is explained by where in the store you put it. All right, so if you're a sales manager for Citrus Clean, then obviously you're thinking, hey, I really need to hone in on where I'm placing my Citrus Clean. All right, that leaves 12.51% of the total variation in Citrus Clean sold unexplained. Okay. So, using the Fisher analysis, is there a difference between near the beer and near the bread? All right, so we have a null, mu bread equal to mu beer, and an alternative, mu bread not equal to mu beer. All right, we want a p-value. All right, so we scroll down to our Fisher individual tests for differences of means, and we look for the pairing near beer, near bread. That's our first one. Scroll over and get our p-value, 0.0540. All right, what's our decision based on that? Since 0.0540 is greater than 0.05, we fail to reject the null. What's that mean? There is not enough evidence to conclude the means between near the bread and near the beer are different. All right, so now to our loaded questions. Using the Fisher analysis in the interval plot, is there a best location? All right, let's go down to our interval plot. All right, so we look at our interval plot here. We look for the maximum, and we see that's other cleaners. Other cleaners is well above the other two. But is it significantly different from them? To answer that, we have to scroll back to our t-test here, and we look at the two pairings with other cleaners. Other cleaners near the bread, the p-value is less than 0.001, which is less than 0.05, so we can assume they're different. Other cleaners near the beer, less than 0.001, so we can assume they are different. All right, so yes, other cleaners is significantly different from near the bread and near the beer, and it sits atop them, so we can definitely say the best location is near other cleaners. All right, using the Fisher analysis and the interval plot, is there a worst location? All right, so it appears as though near the beer is the worst location because it's the lowest. But we already know from our previous problem that near the beer and near the bread are not significantly different. All right, because of this p-value, 0.0540, these two are not significantly different, so we cannot say there is a worst. No, there is not a worst location. Right? All right, well, hopefully this helps to explain how to do the F-test for variances and one-way ANOVAs. At this point, you should be ready to do the homework.